Hi, welcome to StatStuff. I'm Matt Hansen. In this lesson, I'll do a quick, high-level review of some of the fundamental concepts associated with statistics, such as population data versus sample data, distributions, central tendency, spread, etc. We'll go into much more depth of these concepts much later in the measure phase. There are no prerequisite lessons for this one, so let's start by comparing population data versus sample data.
Well, we would say that a population represents every possible observation. Now, it's very ideal if we can measure an entire population, but it's also very rare when we have that opportunity. And quite honestly, it's not necessary that we have to always measure the entire population. Now, compare that to a sample. A sample is basically a subset of the population. That is, it's generally a fair representation of what that population should look like. Now, there should be an adequate sample size that we can acquire that allows us to make appropriate inferences about the population. But the differences between the conclusions that were coming from the sample versus the reality of the population itself is actually the risk that it's involved. So, does the sample truly represent the population fairly?
Okay, now let's shift gears and talk about distributions.
Well, for the most part, we expect a lot of things in life to be random. That is, where they might represent like a normal distribution if we were to plot out some measurement of that randomness in a numerical value. Well, if we were to plot it out, it might look like a bell curve, where it's what we call a normal distribution. So for example, if we're trying to measure the age of employees across an organization, or possibly with another continuous or variable type of value like temperature in degrees across many different rooms within a large building, well, those kinds of things we expect to be somewhat random. There tends to be what we expect a whole lot of data points around the middle, like in this example here, and there happens to be maybe a few that are skewing off to the left or maybe to the right, but they seem to be all in the majority around this middle area with some balancing on the left or the right, and that's basically what we refer to as like a bell curve, where it's normally distributed and there happens to be no skewing that seems to be there. Well, a little bit different from that is what we call a non-normal distribution, where things might look like they're skewed or where there's some bias involved. So let's stretch those examples a little bit further. That is, suppose instead we're measuring the age of employees for just entry-level positions, where we'd expect maybe those entry-level positions will probably have a lot of folks that are a lot younger compared to those maybe in the management or executive level positions who have more experience. They're probably going to have a higher age within our measurement. Or when we're measuring temperatures, we might see some skewing if there are some network server rooms, that is, some computer rooms where there's a lot of high-tech equipment. We tend to keep those rooms sometimes at a lower temperature in order to help that equipment process appropriately and keep them cooled. Well, in that same way, if we're accounting for something like that, that might skew our results a little bit. Well, when you have some skewing or some bias, it will be what's called a non-normal distribution when we plot it out. Now, these might be extreme examples, at least for the other extreme visual examples for the examples of the age or the temperature that was used earlier. But from a visual standpoint, you might see like a non-normal distribution might look like this, where there's a positive skew, where most of the data points tend to fall on the left-hand side with a right tail that goes off to some higher level on the scale, versus a negative skew, which you have a left tail here, and most of the data points tend to fall a little bit toward the right side. So in this type of way, this visually looks like what we call a non-normal distribution, again, where there's some skewing or bias or not the same type of randomness, the normal randomness that we'd expect to see, like what will be plotted in a normal distribution.
Now let's explore how we can interpret distributions through the concept of central tendency.
When we talk about central tendency, it's basically where on the scale most of the data points tend to be centered, or what I like to think of is the central area where most of the data points tend to fall. Well, the type of distribution that we're looking at, whether it's a normal or a non-normal distribution, will really affect which measurement we use for central tendency. So let's walk through a couple examples of that. For a normal distribution, the average or the mean is what we would use for measuring our central tendency. So again, like the example we had before, if this is a normal distribution, the central area where most of the data points tend to fall is around the middle here, and it's generally going to be the average that we would use as our measurement for that central tendency. But the median is also going to be around that same point. It's very often they're going to be equal to each other or very close to each other when we have a normal distribution. So actually we can use either measurement, but most often the average is what we're going to use in those kind of instances for a normal distribution. So there's no outliers on either side when we have a normal distribution, so we don't have to be so concerned about the average moving or shifting because of the outliers that might wrongly influence it. So if we go to the example we had before, when we're trying to measure the age of people within an office building, well, we would assume when we're doing that measurement, it's on a typical random day, and we're randomly asking people the ages for those who are there who might be just employees or customers. And when we do that, we would expect that it might look like a normal distribution. Well, compare that to a non-normal distribution. In that case, again, that's where we had the skewing like we had described in the previous slide. Well, we might use the median or the 50th percentile as our measurement for central tendency instead in that example. So because of the outliers that are represented within a non-normal distribution, those outliers can shift our average. But the outliers do not influence the median. The 50th percentile is always going to be the 50th percentile no matter what your distribution looks like. So it's always safe to use the median when you have a non-normal distribution. However, when you're using the average for a non-normal distribution, it's not going to be as safe because there's going to be some sort of shifting that what's causing it to be non-normal in the first place, like those outliers, they're going to shift that average in a different direction. You might come to some wrong conclusions or end up using the wrong type of statistical test if you don't account for this up front. So if we take our example again, where we're surveying the age of people that are in an office building, if we happen to do that on the day when it's Bring Your Child to Work Day, well, that means we're going to have a whole lot more children present in the building. And if we would include them as part of who we're asking for the age and our representation of our results, well, then we're going to have a lot more children with lower ages in our results, and it's no longer going to look like a normal distribution. It might look something like this example off to the right-hand side here, where we have some ages that are more off to the left, more outliers, lower than we would expect. And as a result, the average might be shifted in that direction when we wouldn't have expected it to. And it's shifted to the left of where the median is, because the median is not going to change. So how could we reduce the risk of this kind of bias in our data collection? We have to be aware of all these possible things that could affect the results. So in this case, we might use the median as a way to make sure we're not accounting for any of that bias if it's a non-normal distribution. Or we might just be careful in how we survey folks to make sure we're only limiting it to just people who are employees or just people that are employees or adult customers, so that way we don't allow for those kinds of things that could create a non-normal distribution.
Another key concept of interpreting distributions is variation or spread.
Well, variation measures how far our data is spread out around the central tendency, again, which could be the mean or median that we're using. So let's say we have two processes that we're trying to run. Process A might be represented about throwing darts at a dartboard, and we might get these kinds of results when we throw 6 different darts. Whereas process B, when we throw the same darts, they might look like this. When we're comparing these two processes, as far as whether we're hitting the target, process A is going to have a higher score because at least one of them hit the bullseye. Then we have a couple that also hit the next ring, and then a few that hit the outer ring. So from a score standpoint, we might get a higher performance from a process represented by process A compared to process B, where it was consistent, but it was consistently bad. It was hitting off the bullseye and not exactly hitting where we wanted to hit in the target. So in this example, though process A might yield a higher score, actually process B is a lot more consistent and a lot more predictable, therefore saying that it has a lot less variation. In that case, that might be actually a more ideal process to have because it gives us better control. So variation really reflects where we have less control and where we might feel the most pain. So the degree of variation affects the degree of difficulty that we might have in trying to correct or fix whatever is causing the pain that we're feeling. The degree of predictability affects the degree of control and comfort we might expect to see. So let me give you an example of that. In our homes, we might have a thermostat and we might try to calibrate it. Well, if we have two examples, let's say the first time I might have a thermostat that one day I set it to 72 degrees, but if I have a thermometer sitting next to the thermostat, I might see that I set it to 72, but at one point it's at 75. At another point it's down to 68. At another point it's moving up to 71. Then it's jumping down to 67 and back and forth. It might be averaging somewhere around that comfort level that we might want to see around 72, but again, it's moving so much that we're feeling the pain and discomfort of that movement. However, if I were setting it to 72 and it was constantly hitting 75, or maybe I set it down to 70, but then it was constantly hitting 73, well, in my head I know it's 3 degrees off consistently. So if I wanted to be able to fix it, it's a whole lot easier to fix in that second situation because at least it's consistent. There's little variation. It's a lot harder in the first circumstance because there's so much variation. It's hard to tell what's really wrong with the thermostat to try to control it. But in the second situation, if I really want to have a quick fix for it, all I have to do, if I want 72, then I just adjust it down to 69, knowing that it's always going to be 3 degrees off, and I'll hit the desired 72 level that I'm looking for. Or another example is there is a large discount store that uses a slogan, always low prices, always. Well, by very much using that slogan, what they're trying to get across to the customer is that there's a lot of consistency as far as how they're offering low prices. It's their way to communicate to the customer saying that there's a little variation in our prices. So you can trust us, we're going to be very consistent as far as offering the lowest prices. So if that's your goal, you know you can always achieve that goal by going to our store to achieve those lower prices. Well, it's very clever in the way they communicated that because they're trying to reinforce the pain that we might feel if we're going to different stores and we're experiencing a higher price one day and lower price at another and not really knowing or trusting what type of price we're going to get. They want to be able to minimize that kind of pain for the customer and give the customer the confidence. When they go to their store, they're always going to get the low price. So they're addressing the issue of variation. It's a clever way for, as a marketing tool, to let the customer know you can expect a little variation here, at least from a price perspective. Now, when we try to measure this, standard deviation is usually the measurement we might use for measuring this type of variation. And the standard deviation is represented by the Greek lowercase letter of sigma. Well, standard deviation is that measurement we would use for measuring variation around the mean. Again, the mean being when we're using normal distributions. But if we're dealing with a distribution that's non-normal, in that case we probably want to use a different measurement. Since standard deviation is using the average, and again when we talked about before about distributions and central tendency, average is not going to be the best measurement for central tendency when we're dealing with non-normal distributions. So in that case, when we have a non-normal distribution, since averages won't work, we probably should not use the standard deviation either, because that's the average distance that each of the observations are from the mean. Well, in non-normal distribution, we probably need to use something different like an interquartile range, IQR, or a stability factor in order to measure that variation that might be around the median, which is a better measurement of central tendency for non-normal distributions.
All right, now let's go a little bit deeper and talk about defining defects and sigma levels.
Well, we would say that defects are anything that goes outside of the customer's requirements, and we would define the customer requirements as the VOC, or voice of the customer. So if the customer requirements and the way that we define those, it would be measured in terms of tolerances by a lower or upper specification limit, or an LSL or USL. And anything that goes beyond the lower spec limit or upper spec limit, again, which defines the customer's requirements, is considered to be a defect. So let's illustrate that here. Let's say we have some sort of scale, and along that scale we might plot our data points to create a distribution of our performance, to measure our central tendency and how we're performing, as well as the amount of variation we have in the process. Well, within that we might measure, if it's a normal distribution like this one appears to be, we might have a mean as our measurement for the central tendency. And then we might have from the customer's perspective what they define as a lower spec limit and what they define as an upper spec limit. So anything that falls within what the customer expects, the lower spec limit and the upper spec limit, anything within this range is going to be considered to be acceptable and good. So that's what we're aiming for. So that means that anything that falls outside of this range, beyond the upper spec limit or below the lower spec limit, all those kinds of things are going to be defects. Now, when we're doing this type of measurement and evaluating our process like this, we use a sigma level to measure the number of standard deviations that fall between the mean and either the lower or the upper spec limit. That is, how many standard deviations fit within either side, again, between the mean and the upper spec limit or the mean and the lower spec limit. So a sigma level is what we measure as our quality or accuracy as a measurement towards defects per million opportunities, or DPMO. That's the general term we might use from a Six Sigma perspective. So when we say that something is 1 sigma, we're basically saying there's 690,000 defects for every 1 million opportunities. Well, theoretically that just means that there's a 69% defect rate, or we'll make the inverse of that, of the ones that are successful. That means we're 31% accurate. At a 2 sigma level, there's basically about 308,000 defects per million opportunities, or about a 69.2% accuracy rate. For a 3 sigma level, we have about 66,000, almost 67,000 defects per million opportunities, or like a 93.3% accuracy rate. And then for a 4 sigma level, we have about 6,000 defects for a million opportunities, around a 99.38% accuracy rate. And a 5 sigma level, we have only 233 defects per million opportunities. And we're becoming a lot closer to perfection from an accuracy standpoint at 99.98% accuracy. But when we say something is 6 sigma, we're basically saying there's only about 3.4 defects for every 1 million opportunities. And from a measurement standpoint, that comes out to 99.9997% accuracy rate.
Okay, so what do all these sigma levels mean in a practical sense? Well, let's just compare a couple examples of a 3 sigma process versus a 6 sigma process.
Well, when something again is at a 3 sigma level, that's about 93.3% accuracy. And that sounds pretty good depending on what we're measuring. So if that's that good in meeting our standards, why do we even need to bother pushing for 6 sigma? Again, the 99.9997% accuracy rate. Well, again, it goes back to how much risk we're willing to take and if the customer is willing to take that much risk. So let's compare 3 sigma versus 6 sigma in a couple examples. So at a 3 sigma level, we're basically saying we have about 20,000 wrong drug prescriptions per year, but if we take that at a 6 sigma level, where there's a lot fewer defects, we're averaging then only 25 wrong drug prescriptions per year. It's a huge reduction. At something that's 3 sigma level, that could be 500 incorrect surgical operations per week. But at a 6 sigma level, it may only be 1 incorrect surgical operation every 2 weeks. Now again, the numbers used to calculate these are going to vary and depend on the frequency for these kinds of things like the drug prescriptions and the operations themselves. The point here is though just to show that in this given circumstance, when you compare at least a 3 sigma level versus a 6 sigma level, there is a huge difference. And I don't think any of us are willing to take a whole lot of risk when we're dealing with drug prescriptions or surgical operations. Those are significant things and we want to mitigate the risk as much as possible. So if we can get much closer to a higher level of accuracy, then I think we'd all feel a lot more comfortable because we've mitigated that risk. So if we map this out like on a scale just to reflect how these distributions might show off on a chart and comparing it to each other at a distribution level, something that's at a 2 sigma level might look something like this, where you have still a normal distribution, and this might represent how it's kind of spread out, where you again have a bunch of them that are defects because they're falling outside what the customer's expectations are defined by the lower and upper spec limit. But something at a 4 sigma level, again, it's going to be a normal distribution, but it's going to be a lot more peaked in the middle here, simply because there's a lot less variation. By having less variation, there's a lot less that are falling outside what the customer's calling a defective. And then when you have something at a 6 sigma level, you're only averaging then about 3.4 defects per million opportunities that fall outside the customer's specs. And most of the observations, most of the data points that you're measuring are falling within the customer's expectations and meeting that target. So again, they're all normal distributions in every example, but what makes the difference in how you map out these at the different sigma level shows how peaked or how flat each one of these are, or what's called a platykurtic or a leptokurtic type of distribution.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
What I'd like you to do is to examine some of the metrics that are used in your current organization and ask some of these questions about each of those metrics. That is, which of those metrics do you think are based on sample data versus where you're using population data? And for those that are using sample data, how confident are you that those sampled results are actually reflecting the population? And what are you basing your confidence on? If you think you're very confident, then what's making you feel so confident about it? Is there a way that you can prove your level of confidence with data that the sample truly reflects the population? That's okay if you don't know how to prove that yet. That's actually some of the things we're going to get to later on in some of the other advanced videos talking about statistical analysis. Now, which of those metrics that you're using are measurements of central tendency? Now, what is the measurement that's used for central tendency? Are they using the mean or are they using the median? And also, which of those metrics are used for a measurement of spread or variation? Now, there are very few organizations that actually use variation as a critical metric. So it's not surprising maybe if your organization doesn't. But if your organization doesn't, then what do you think some of those risks could be because they're not allowing for that measurement of variation in the business?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.